live. Double check.
Checking. Yeah, we are live. Let's do it.
All right. Hello and welcome to Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions in the episode. We'll get to it. Also, we're in the process of making YouTube shorts, sub 1 minute explanations of your choice. So if you have any suggestions, do send them our way, and we'll definitely take into consideration. All right, let's get to it. So, Tim and Mikey, last time we had talked about an interesting role that the Higgs boson plays, typically when people, or rather the Higgs, and we'll be more specific what that is. And when most people think about the Higgs, they think of the Higgs boson, the particle that the giant collider in Switzerland, CERN, LHC, was trying to discover. And we talked about how it would essentially gave us the universe that we know, which essentially gave rise to us, which we can then observe. And so kind of say it's a creator. We hinted at the end of the previous episode that it might actually be our own undoing. So maybe it might be helpful, Tim or Mikey, whoever feels inclined, to go over briefly what we talked about the previous episode and how it segues into what we're going to talk about today.
Yeah, sure. So last week, we talked about a specific event in the history of the universe, right? So, and I guess I just wanted to stress that this is arguably like the biggest, deepest question you can ask, right? I would say it's like the main goal of cosmology, certainly, but maybe also just of physics, is like, can you kind of like an archaeologist, like reverse engineer the way that the universe got to be the way it is now? And one of the first things you notice in that is that the universe did have a beginning. So there was a moment of quote unquote creation. And then after that, there were several important steps that we know were required to get the universe from its initial state to the one we have now, where life is pleasant and complex chemistry exists and planets can form and things like that. And last week we talked about the Higgs, and we argued, right, that it's like, well, I guess in previous episodes we did a lot of we covered a lot of these different important events that were critical for the formation of like structure in life. And last week we covered the Higgs, which is responsible for the creation of light. We argued that we're beings of light and that light did not exist always in the universe. The universe was filled with this Higgs field, which we said you could imagine like a fluid. And at a certain point, this fluid froze and light appeared in the universe. So that is what we mean by creation, I guess, what Sahil referred to as creation. And I would argue that that's like a pretty, arguably the most important moment in the evolution of the universe for the development of like life. And so I guess today the goal is to talk about what the eventual fate of this might be in various scenarios.
Yeah, so I think
I also remember. Oh, I just want to make one quick comment, Tim, and then feel free to go ahead. So Mikey, that you had mentioned in the previous episode that like at that moment when that happened, you could effectively say like, how God said, "Let there be light," kind of a moment. Is that fair to say?
Yeah, I mean, like, the T-shirts that people wear that have like Maxwell equations and God said, "Let there be light," like that would be the moment at which that happened. So, the whole 7 days thing is a little questionable, but you could literally imagine that it was like a multi-step process, and then the last step was like, "Let there be light."
Got it. Go ahead, Tim.
Oh yeah. I was just gonna add that the follow-up is that this event that happens in the early universe, it could perhaps happen again. So that's what we're going to cover today. And what happens when it happens again it will be cataclysmic. So in a sense, the Higgs field gave rise to our universe, but in this exact same way, it could take it away. So that's what we're going to talk about, the how and the why.
Yeah, I think nothing like a very morbid kind of opening to get us started. So
I just thought of my closing statement. So happy.
oh, excellent.
Okay.
Yeah. And also, if any of you guys, listener, have watched the documentary Particle Fever, or have visited CERN, the collider at Switzerland, or the European Agency for Nuclear Physics Research, they have a statue of Shiva, right? And Shiva in the Hindu god, I think I'm not familiar with it, represents the creator and the destroyer. And I think if you watch the movie Particle Fever, they also make this analogy, like the Higgs field can be interpreted as responsible for creation and, in some sense, perhaps destruction at the end. So for those of you who have seen the movie and or are going to CERN at some point, definitely check that out. It's interesting.
Yeah, definitely interesting. They reference an Indian mythological being or entity in there, but it makes sense. It makes sense from what I see. I mean, there's a lot of parallels as Mikey can attest to as well between religious texts and like quantum mechanics and whatnot. If I remember in our previous discussions.
Let's go for Chuck Capra. I think his ideas are being validated by recent findings.
I see. So so I wanted to dig into essentially, the basis of this episode is like, why do we believe that the Higgs can it can sort of essentially ruin the universe? It seems like the universe appears to be in a stable state, or what it's doing. I mean, yeah, it's expanding, and I mean, but that doesn't seem much like a destruction aspect. It seems more of kind of like just heat death, like slow, gradual thing. Is that similar to the Higgs, or is it worse? Like, let's get some intuition on this.
Yeah, so I think now I'm thinking about it. I think it's really good to try to piggyback as much as possible off of the last episode. We can recap it. We'll try to be brief. But last week we made the analogy that this act of creation, the let there be light moment, is kind of analogous to, let's say, water freezing. If there's fish happen to be swimming in the water at the time when the water freezes, that'll be catastrophic for the fish, right? But we know that it's not just water and ice, right? Like there's actually like a gas form too. So why are there these kind of like quote unquote three phases of matter, which is not even true? Why are there these certain boundaries where it seems like the substance changes its properties drastically and suddenly? Like when you go from gas to water, as the temperature cools, suddenly the properties of this substance changes drastically. And then again, as the temperature cools, you go from water to ice, and again, the properties change drastically. So it's kind of hard to guess a priori what's going to happen when you lower the temperature. For the most part, it might just be a smooth, cool, gradual, evolution. But you might run into a wall where at some point it just, something drastically changes. And that's really what we're talking about here.
Although for the Higgs field, it's not so much temperature. Temperature is quite low in the universe anymore. But
yeah, but it's getting lower, and that's what may or may not trigger, right?
Well, I think it's so what triggers it? It's a different question, I would say. But
what triggered the let there be light moment was the reduction in the temperature.
Right, but for the potential second one, it might be something different. But I would say stability of our universe is an observational fact. Like it's been stable so far, but it could be unstable. Maybe we went through a few more, 10 times the age of universe. It's not guaranteed that it needs to be stable. And in fact, people can do this calculus. You can extrapolate, given what we know about our universe, to see how stable our universe is. And intriguingly, there are some hints that our universe may not be stable after all.
What I mean, I guess what would be those hints? Because I don't know. I mean, is the length of the time scale important here? Like if I look, a billion, trillion, gajillion years from now, then it won't be stable, or because I mean, from one moment to the next in my lifetime, the universe has stayed like essentially the way it is.
Yeah, I mean, of course, we can't wait forever. Like you can't run an experiment and wait a quadrillion years. That's impossible. But what we can do is make some inference. What we know about the Higgs field is that the Higgs field has interaction with other substances, and that actually alter its behavior. I guess the analogy is kind of like, if you have water, you add some salt in it, it might freeze at a different temperature. And in the same way, the way the Higgs field works is it interacts with other stuff like quarks and electrons, and the quarks and electrons got slowed down by the Higgs field. You can think of it as a repeated collision. It's kind of like light traveling in water. It gets slowed down, and particles like electrons and quarks, if they travel in our universe, which contains this Higgs field, they can bump into the Higgs field kind of over and over again, quantum mechanically, and that gives them mass. But in return, they also affect the Higgs field itself. There's sort of a little bit of a recoil effect because interaction doesn't happen in isolation, right? The Higgs field endow particles with mass, and as a result, the Higgs field itself also feel a little bit of recoil. You can think of it that way, like all these particles bumping into the Higgs field. That kind of can drive the Higgs field to move one way over another. Kind of like how adding salt to water can make it melt or freeze a little bit more. And that's what we're talking about. When we look at these effects, there are hints that maybe things, might go haywire.
Is there, I guess with, maybe a simpler particle like the electron or something, is there a way in which you could expand that the properties of a particle change depending on its interaction?
Wait, can I just back up? Because I just wanted to say, because you asked a question before, and Tim was talking about how we can't really know how long the universe will last, right? And you were kind of alluding to the question of how could you? But really what we're talking about here is making a theory. That's what physicists do, right? Like we theorize. So if you have a theory, what we have right now, when we talk about the theory of how the Higgs works, is a very, 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 very rough theory of how the most basic part of it works. There's thousands and thousands of theories about how the details might work once we look there, most of which have since been invalidated. But really, that's what we're talking. So when if you have a detailed theory of how the Higgs works, on the inside, which we don't have right now, then that might tell you something about how much more time we have. And I think the saltwater analogy is really good, right? So let's say you find yourself in a gaseous state, or let's say we find ourselves in floating in a liquid, right? And we realize that the universe was hotter before, so that liquid must have been a gas. At some point, the temperature cooled and the gas became a liquid, and that allowed, I guess we're fishes in this analogy, so that event, the gas cooling into a liquid, that gave the fish an environment to live in, right? And now these fish became smart and they became scientists, and they want to know, geez, the temperature is still dropping, so when is it going to freeze? When are we all going to be dead? Well, that depends, right? If there's salt in the water, then temperature might drop very, very low, right? If you're actually swimming in alcohol, maybe, I don't know, everything will freeze eventually, but right, depending on your theory of what kind of water you're swimming in, that determines when, if ever, the substance that we're swimming in might suddenly change in a catastrophic way.
Do you want to? I mean, I think this may be tangential, but I feel compelled to ask you to mention it. Is the Korean soju the drink?
Oh yeah. Well, that's wait, was that That's actually a technical detail, right, that we're trying to explain. But we should tell the story now because
Yeah.
but for any fans out there who may have ever enjoyed the Korean liquor called soju, you have to try this trick next time. It's actually the best way to enjoy it, and it's going to be relevant to the discussion later. So we can just plug it now. But if you take a bottle of soju and if you put it in the freezer for between 1 hour and 2.5 hours, let's say 1.5 to 2.5 hours, you'll notice something very strange. You'll take it out of the refrigerator and you can shake it, and it's a liquid. It's just it doesn't look any different. It's just colder. But then if you hit it with the palm of your hand really hard, in a fraction of a second, the whole thing will just turn into a slurry of ice mixed with liquid. And that's actually the most delicious way to enjoy it. And it's just impressive, so it's a good party trick. But yeah, when we're talking about the analogy of us being fish in the water freezing, that is actually a closer analogy to what might happen than just the water freezing, just plainly on its own accord.
Could you say we're fish swimming in soju?
Yeah.
I think it's like a super cooled or super heated. But keep in mind that the temperature here, there's no good analogy for the Higgs because the temperature isn't exactly relevant. But
it is kind of relevant. It determines the fluctuations with the baseline of energy and where the fluctuations.
Right. It does. But the at least at the current universe, the temperature is so low that it doesn't impact it very much. But in the beginning of the universe,
constant for in the span of humanity's time on Earth.
Yeah, but basically the idea is the Higgs field right now might be in a very precipitous state. That maybe if there's enough jostling, I don't know, some aliens or whatever, somehow like mess up the Higgs field in one region, it might just flash freeze or flash boil, whatever that is, and causes a cataclysmic change to the entire universe, right? And that's what we're talking about. If there's is this meta instability, such an event could happen.
Yeah, to go back to the soju analogy, to describe the physics of how that works, basically what's happening when you put this liquor into the freezer for just that amount of time is it's basically right in between. It doesn't know if it wants to be ice. It doesn't know if it wants to be liquid. It hasn't made up its mind yet. And even the slightest like feather or like you blow on it and it'll like go in one way or the other. And it always starts at one point, or maybe it might start at multiple points, but it starts at points. When you hit it, there might be one part of it that decides it wants to be ice, and that'll communicate out like an expanding bubble. And that's actually what it would look like if it happened in our universe. It would probably start at a certain point, and then a death bubble would just expand out from the center and consume everything. They ran the scenario. That's what would happen.
I guess like how do you know what's the simplest way theoretically to explain like how do we know that this is even a possibility because it hasn't happened yet? Obviously, you're getting this from some experimental data. This is being assessed. Like what are you using to actually make this assessment? Like,
well, if you think about it, isn't it more generic that it will happen again? Like, we know that it happened a few times since the universe was created. Like, let's say it happened 4 times, some kind of freezing process or phase change, as we call it. Then you have to explain why that number is 4. 4 is a weird number. Usually things happen either 0 times or infinite times. There's usually no in between.
I think an analogy with hiking, it's a little bit more. Maybe it can help the visual aid, right? Like, and usually when people describe the Higgs field, it's kind of like a rock rolling down a hill, like the rock is rolling down a hill, and now it hits a little dip on the mountain, and this might not be the final end of the rock. If someone were able to push the rock over like a little bump, it might roll even further, and it might roll a lot further. And when that rock rolls a lot further, it has energy in that rock. And that could cause catastrophic damage. So how do we know the rock, which is the Higgs field, has reached its terminus, the only thing because we don't have a global view of the entire mapping or the entire hiking map of the way the Higgs field is, we can only extrapolate. So for example, if we know where the Higgs field is. If you like the analogy of the rock, you know where the rock is because we live in that universe now. You can kind of look around you, which way is up, which way is down, and just scout out a little bit and look a little further, right? And
is this a hill that leads to death?
Yeah, exactly. Is there like a cliff beyond, or is it just pretty mellow, just like a plateau, or is there like a infinite abyss, right? So scientists are able to do this extreme extrapolation, and keep in mind that the extrapolation, it really is extreme. It's almost like you look at the hill, and it tilts slightly upward, but there's a trend that this tilting upward is decreasing, right? So if you do this extrapolation, you actually see, given all the data we have, you actually see that it tilts up, but the acceleration of it tilting back down will eventually overwhelm it. So it goes up, and eventually it's going to go back down.
I guess I want to get a bit more intuition about this. So it makes sense, the picture you talked about, is if the Higgs field is like a rock in this location. What are all these hills? Like, I mean, obviously this is like you're taking an abstract concept and trying to give an analogy, explain it, but like what is this hill? Like, why is there like a minimum? How do I wrap my arms more around this?
Yeah, I talked about this last week a little bit, but the theory space, right?
The way to think about it is you can think of the Higgs field in an abstract way. It's an abstract number, like a dial in an oven, but it's abstract. The physical realization of it, you have to think of it in terms of its physical effects. So what happens when the Higgs field gets larger, right? When the Higgs field gets larger, it means that the electroweak forces are weakened. They are even more screened. And certain particles pick up more and more masses. Basically, when we say, oh, the Higgs field gets a little larger, we mean what happens if the electron is a little more massive? What happens?
Wait, every particle that we know gets more massive, right? We don't know any particles that don't.
Well, every particle that interacts with the Higgs field will get.
We don't know any particles that don't, right?
The
neutrinos?
The neutrino.
Yeah, that'd be crazy. Yeah,
neutrino,
there's no vector-like fermions.
Neutrinos and gluons. I mean, those are unincluded.
No, but everything that has mass got it from the Higgs. So everything would increase in mass.
Yeah, so basically, if we try to run this thought experiment, imagine someone is able to dial up the masses of all these different particles. It would take an immense amount of energy. These are the hills, right? You can't really do that. It's too hard. Like imagine you're able to whack the Higgs field really hard, and then it increases the masses of all the particles. Usually, it takes a lot of energy. But basically, if there's a cliff beyond, it means that at some point, if you hit it hard enough, you actually get the energy back. It becomes exothermic. It actually is energetically favorable if you do that. As long as you wax it hard enough that there's a bubble of death that gets created, then all of a sudden the whole thing, like, it will fall like a domino, basically. So all of a sudden it's like, oh, whoops. Well, guess what? This is the universe like that. Right, and it's the whole dominoes falls. So that's the analogy we're talking about. This is really like we're talking about in theory space, which is a little bit abstract, but really we're talking about the masses of all these different particles.
So like if I take the Higgs field, maybe you're talking about an average value or some kind of value associated with it, and I imagine that as a rock at the bottom of this like hill, and there might be a further bottom. What would like push it over the hill? Like what? Because if I take a rock as it is, like I look at a rock, it's just gonna like be there, unless somebody pushes it up or something. So what would give rise to it like going down?
In order for you to believe the answer, you would have to believe that things can go through walls, which is a inescapable conclusion of quantum mechanics. But it sounds weird, but it definitely happens, and it will eventually happen if it can happen. Uh, yeah, that's literally
Yeah. So
right.
yeah.
Yeah. So I mean, I guess we can say this, right? So when you talk about like the oh wait, shoot, is this gonna be more confusing if I describe tunneling as going through a wall? Because you were asking about like what do these curves mean, and we gave some abstract answer about theory space.
Mhm.
But one way to interpret it is actually as a physical wall, right? Like as let's say there's like some like literal ceramic, I don't know, stucco wall here or something. As I go through it, the amount of potential energy stored in my muscle that will be required to break this um, wall can be represented as, kind of going over a hump. And then once I actually break the molecular bonds of the wall and I go through it, that's when I get over the hill.
Mm.
I think we could have a more visual answer. It's kind of like if you think about the concept of virtual particles popping in and out. In quantum physics, things are just fluctuating. You can kind of imagine everywhere in the universe, there are actually these small pockets of doom occurring everywhere. Like maybe in this region, there might be a tiny pocket where the Higgs field is a little different. Like the electron is a little more massive. And in order to do that, the universe has to borrow a little bit of energy to do that, right? Because it takes energy to increase the masses of a lot of particle. So chances are, when this happens, because the universe is in debt, it doesn't like that. It's gonna disappear real quick. So a lot of times it's disappearing everywhere. There are little pockets of doom appearing and disappearing, appearing, disappearing everywhere. But occasionally, these pockets of doom might unite. Maybe two just happen to appear in the same place. Then that little pocket of doom gets a little larger. And when it gets a little larger, it's a little harder to disappear anymore. But still, most of the time, it just pops in and out. But at some point, eventually, just by chance, you might have many, many bazillion different pockets just all happen to fluctuate in that same way. And when they unite, they might realize that, oh man, this is what the universe like. This is lower energy. And then this pocket of doom become unstoppable. It might try to shrink, but it got so large that it just keep growing. Kind of a bit like a black hole. I don't know if is that a good analogy? It would just keep growing. But at the speed of light, though, it will swallow everything in its path. The bubble of doom will just expand, and eventually it will just destroy everything.
So can I think of this as like there are these quantum fluctuations happening, and eventually, if you wait long enough, there'll be a quantum fluctuation so large that it'll push this like figurative rock over the hill, and it will like start rolling down. And as it's like rolling down, this is that the concept of death bubble, or does it actually need to like hit another minimum for the death bubble to happen?
I think the moment this bubble gets large enough, the death bubble happens. Because the physics of this phase transition is complicated. Because when a bubble is formed, you have to look at the dynamics of it. The walls are moving. There's surface tension in the wall, you can calculate. And the surface tension will try to shrink it. But the doom bubble will also try to expand. Most of the time, the surface tension wins when the bubble is small, so it disappears. But yeah, the moment the surface tension stops winning, that's when this death bubble will grow. It will become unstoppable. So then you can have different bubbles forming in different patches of the universe, and eventually it's kind of like boiling, really, a bit.
No, it's more like the soju thing, like, I guess.
Yeah, maybe.
So like to describe what Tim was saying in terms of liquor, like when it's more dramatic, I guess. But like it's when you hit the bottle, like I said, like initially it's in this state where it doesn't know if it wants to be water, doesn't know if it wants to be ice, and when you hit it, probably like in 100 different places, they'll decide at that place that they want to be ice, and then it'll take over the whole space eventually. But only if you hit it hard enough. If you hit it light, it's not going to be enough to push over the barrier, and it's just going to stay water. You got to really give it a good smack.
Is there any sort of mechanistic explanation of like how this kind of percolates, like why everything just decides to kind of fall in line, like taking the transition from like liquid to ice, for instance? I don't know if you guys know.
You mean why it's a bubble, or?
Yeah, like how is it like just that it, I guess, yeah, how is it that it like rolling down will just sort of like, I guess, percolate throughout?
I,
Would there be
I,
a
That's harder
range?
to
Like
visualize,
why
right?
does that have to percolate throughout the entire universe? Like what if you
yeah,
had like a soju bottle, like,
Mm.
that's just like immensely huge, and you put in this giant like
Yeah.
freezer and you hit it really hard?
Uh,
Will that actually percolate through the entire universe, or would it like a part of it would kind of die out? Like,
that's a good question.
I
Might
mean,
depend on how fast the universe is expanding.
it depends because yeah, because the universe doesn't have an exact boundary. So what will happen? You're
mm,
gonna have patches. This is gonna be like a fractal like structure, right? Um,
mm,
and also remember that you can't really have a global view of the universe. So you can't. I don't know how to even describe it, but the physics of these bubbles forming is very similar.
mm,
In to like let's say water freezing or boiling, right? The physics is similar. You have you have multiple forces fighting each other, and in thermal physics, instead of having quantum fluctuations, you have thermal fluctuations, and then you have thermal physics, and instead of energy, you have entropy, and then
mm.
things can spread like that, and we use it to describe water boiling and ice freezing.
Doesn't it
That's
work? But doesn't it happen in ferromagnets too? When you have like the frustrated
yeah,
magnets,
something like
like
that,
like
but
like everything spreads out from its location until it encounters something that disagrees strongly enough, and then you have patches.
yeah.
Yeah. I mean, also, okay, so I guess maybe one saving grace could be inflation, that there's certain, if you go far enough distances, they're expanding faster than light. So
Yeah.
if you had a death bubble that was forming far enough, like really far away, it would
Mm.
never reach us because the universe is just expanding.
Yeah, yeah.
Well,
Although
no,
there's one.
wait. The death bubble goes at the speed of light, right? So, well, the
Yeah.
universe. Yeah,
The,
so
the
that's true.
But
That's
the
true.
spaces expand. I mean, does
That's true.
it
Yeah.
just go? Yeah. I mean, is that wrong? Is that wrong, or is
No,
it?
that's
no,
right. That's right. I had to check it
I
though.
think you have to do the calculus because if the phase transition happens, imagine this: a death bubble comes in. There's so much energy there. This is like increasing the mass of certain particles by like 9 orders of magnitude. I think it's probably more than that. Like imagine the electron all of a sudden becomes a trillion times heavier, and the proton also becomes like a trillion times heavier. Everything
Mm,
would just start like breaking apart, right?
What? I don't know. I have to think about that actually.
Right, but when that happens, there's going to be so much energy. Those energy can gravitate as well, and that might
mm,
affect the rate of expansion in the
mm.
universe. But
The energy density would increase dramatically. Yeah.
yeah,
I
that would. It's not clear what would happen. It would have to. There will be some interaction with gravity, but that's not obvious. What would happen? We don't
Yeah.
know. I
No,
would
but
say.
for sure
so
it's true that if the cosmological constant was high enough, namely if the universe was expanding at such a tremendous speed, it would certainly outpace. You get these disconnected patches that wouldn't even talk to each
mm,
other, right?
Right. Yeah, but things like
yeah.
galaxy and planets are doomed because those don't fly apart, right? The Earth,
Well, in the patches, maybe, but
yeah,
between the patches, definitely not.
yeah. So it will still be a death ball. Like the
Yeah.
cosmological constant will not save us from the death ball. I think.
Well,
So
if the death if the
mm.
death bubble is happening sufficiently far away, then it might save us from that one, right?
Maybe, but the nearby one we won't be safe from that.
Yeah. Well, what's nearby mean?
So, okay, so I wanted to clarify something. So this process of this death bubble forming, you mentioned that things will get a trillion times heavier. I thought like this is the rock is rolling down. So you mentioned if the rock rolls up, that means masses will like definitely increase. But if it's rolling down, doesn't that mean the Higgs field is getting quote unquote weaker or something
Oh,
like
we're gonna
that?
get
And
into the
so it
negative
actually get
positive
less
mass
massive?
discussion.
Yeah,
I don't know. Like,
That's
yeah.
all you, Tim. That's all you.
no. Actually, that's not true. The height of the height of the rock is the energy that it requires to roll it. The location of the
Mm,
rock is what the mass is, basically.
Oh yeah.
Yeah. So imagine, I don't know, along the trail, the Higgs field is at the beginning, then yeah, the masses are not very large. But if all of a sudden at like a mile marker 10 miles out, there's a cliff, the rock might just like, if you push that rock to that cliff, oh man, hell is gonna break loose, basically. So now all of a sudden things will get bazillion times heavier. And there might be no coming back. There might be nothing to stop the rolling. It might be like a cliff that goes on forever. We actually have no indication that this cliff will end. Actually, it's a complete
the
runaway.
only indication we have is that, as we said in previous episodes, there are no infinities in physics.
Yes.
So we have a religious belief that this can't go on forever, because that would be
right. It's probably it wouldn't go on forever, but Yeah.
Okay. So just to make sure I understand this, the height is the energy of the field, and the distance. If I imagine like there's a center point of this like map that you're abstract map that you're talking about, that if I'm at that center, then masses are basically zero, but as I go further away they start increasing. I guess why would that be different? Like, why is the energy in the field different than the masses of the particles? Like, how can I think about the relationship between those two things?
Generally, it takes energy to make the masses of particles different. But you can't just increase the mass of an electron. That takes a lot of energy, generally. At least like E equals mc squared. So naively, it takes energy to increase the mass of certain particles. But because the Higgs field has interaction, and specifically to top quark, somehow there's a negative feedback loop that actually makes it okay to increase the mass by a lot, right? And this is not obvious. And we don't know if it's really true either. This is an extrapolation.
To be clear, we don't really think this is true. It would fly against the face of like everything, all of the common wisdom. That's not to say it can't be true, but yeah.
Yeah, let's just say it's a plausibility. And it's actually interesting that you can draw a phase diagram of the mass of the Higgs boson and the mass of the top quark, and depending on those two masses, the universe might be stable, unstable, and there's a very thin strip of metastable. And it just happened that, I don't know, by chance or whatnot, we are on that thin strip of metastability. And people don't exactly understand why, but it's just what the numbers came out to be. Right? Or maybe the calculation is wrong. Who knows?
Assuming that there's nothing else, there's no other salt in the universe that could affect the freezing temperature, right?
Yeah, basically.
Yeah.
So, okay, one question I have is like, say you take this example of the rock on this hill, and I like hit it, but it rolls up and then rolls down to where it is. Like, but it rolls up like noticeably up, but it doesn't go over that hill and then slides down death bubble and whatnot. What would it be like? Would there be like still a bubble that just increases, like two bubbles emerging, like one that increases the masses of everything, another one that decreases them back to normal? Or like, how would I think about that?
Yeah, we're talking about quantum fluctuations. So like, right, if you wait like a Google number of years, you're going to get anything. You get a Boltzmann brain, right? So these little, like, I think it's just the way you described it, but yeah, just these very transient yet localized violence.
Yeah. So if it happens quantum mechanically, let's say a bubble, just the Higgs field goes to the peak, but not quite, then it would just return all the borrowed energy. You basically get a lot of virtual particles popping out and then disappear. So nothing would happen.
It would be violent. No, well, if it was big, it could be potentially violent if you waited long enough, right?
Yeah, but then it will cancel out, kind of, right? but if you're doing it artificially, let's say you have a massive collider, you're like, you know what? We're anarchists. We are evil scientists. We want to see if we can break the universe, right? And you have an accelerator to smash the Higgs field as hard as humanly possible to try to destroy it, right? And if you couldn't quite get it, you just get a lot of particles, a crap ton of particles that comes out. You might get cancer or destroy a planet, whatever, but probably won't destroy the universe. But if you do happen to hit it beyond, then maybe you can create a bubble of destruction large enough and then unleash the demons of the runaway vacuum decay. Then you could destroy the universe.
Which is exactly why if you do the soldier trick, you have to really give it a good smack.
I see.
Yeah.
So
I actually gotta go now,
let's
but
talk-
should I just give my closing statement here? I don't know.
yeah, go for it. Go for it.
Okay. I was just thinking, like, at the beginning of this episode, like, it's entirely possible that our existence is only here to enable the next phase of existence, which is going to be the beings that live in the ice after it freezes and we all die. And I just think we should let go of our egos and consider that possibility and be okay with that too.
All right. Well,
Cool. All right. So I had to leave, but I'll sign
I'll
off
see
now.
you in the ice.
Yeah.
So I guess, Tim, one question I wanted to ask you was, let's say it does go over the hump and it starts like, just run away, just starts going down. Does that mean everything is just going to get heavier and heavier and heavier until it all becomes black holes, or like what happens?
It's plausible. Yeah, that is unclear. With that amount of mass coming out, there could be a collapse into black holes. It is quite likely. But that also has to interplay with the cosmological constant because if this were to happen, according to our estimates, it's gonna be like trillion times. I don't even know the exact number. Many times the age of the universe. So even though there's a tiny chance that it might happen right here, right now, don't worry. This is way smaller than the chance that you might get hit by lightning or whatever. So no need to worry, right? But if it does happen, this will be many eons later. And what the universe looked like at that point, we are not sure. Assuming the theory is correct, even.
Yeah.
But yeah, if it's run away, there might be no recovering of the universe. There might be no more interesting structure to form. So in that sense, there might not be planets or galaxies after the fact. Who knows?
So so you mentioned interesting structure. Would it be that like there would also be new particles that would come into existence, or would it just mean that gravity would be so strong that no interesting structures can form?
Well, at the most basic level, if you just take the standard model as is, then there will be no new particles. But all the particles that we know and love will pick up different properties. The masses will all of a sudden become super heavy. And I'm not sure if protons or neutrons will be stable, although those will be super heavy. Atoms might or might not be possible. Chemistry might have to be drastically different. It is not clear. Like, maybe there could be a second level of creation, like beings that are made up of these really heavy versions of protons and neutrons and atoms. I'm not sure. One has to think really hard. Yeah.
Yeah, but these beings wouldn't know that they're like heavy. They're just
of course. These beings would be like, what's 100 trillion degrees? Although their units probably would be different, right? Their masses would be like, whatever.
I see. So there's possibility for structure to form, but it's just, one can only imagine. There's like, it's not clear at all what this would even look like.
Yeah, but I mean, our existence will be completely erased. I don't even think there'll be any traces of it.
And so when you talk about like things being, I guess, I don't know if you mentioned ripped apart or what the word choice was, but like, as this bubble is coming, like what happens to my particles? They just like, I don't know, does everything just suddenly attract each other and they all kind of clump up, or like, just what?
Yeah, so first of all, the energy is basically the energy. If this was true, of course, keep in mind that this is speculative, right? So the Higgs field is metastable. There's great amount of energy stored in it, right? And if this bubble of doom were to get created, there will be a lot of new particles that get created just because there's so much energy, and the walls of the bubble will be highly energetic. And this might be somewhat similar to the creation of the universe when matter was first created. Remember we talked about the inflaton field, how matter could get created. So imagine my hand is right here, and there's a bubble of death coming toward me. It's gonna move at the speed of light or near it, so I won't be able to tell. And that boundary of the old universe versus the new universe would have a tremendous amount of high energetic particles. So probably as it goes through, it would just vaporize whatever the heck I'm made of. And just, like, all the particles that I'm made up of would just be unrecognizable. And then after that fact, after that fact, the universe will just be a plasma again, with not much going on. And maybe as it cools down, if the Higgs field is not runaway, maybe it was finally stabilized after this cataclysmic event, and maybe there will be a second stage of the creation of nuclei, protons and neutrons, atoms, and then maybe new era of planets and galaxy. Of course, super speculative. These will be heavy, way heavier. Galaxies made up of things that are trillions of times heavier. I don't know what happens then.
I see. I had a question for you, but now it's kind of escaped me.
But I do also want to add that it is plausible that we might not be the first kind of structures in the universe either. Maybe the universe has gone through something like that in the past. Maybe we're already layer level 2 beings,
Yeah, but wasn't the universe a lot hotter? So how can it it seems implausible for structures to form when when it's like really, really hot or
yeah. So in order for that to happen, you probably have to have very non-standard cosmology. Like this is going to be more fringe science. Like this has no experimental backing. But I would say this is a plausibility, but there's no evidence to suggest it's true. But if it were to have happened, let's say through the inflaton, whatever, maybe not the Higgs field, we might not see traces. Maybe we might not see traces of it at all, because it was erased.
I see.
So we don't know.
I remember my question now. It's a little bit slightly tangential. I mean, we don't have to spend too much time on it, but out of my own curiosity, would you say the death bubble is akin to like the firewall from like black hole's firewall paradox? I know that has to do with like lack of entanglement between two regions, but I'm curious like if the similar thing applies here. Like, will the death bubble be entangled with its environment, or is it just like no, I'm gonna be completely different?
No, I think it's different. I mean, it doesn't have the death bubble doesn't involve gravity much at all. It is just a really energetic thing. It's just a wall of energy with particles getting created. So
so it doesn't have to do with entanglement even.
Probably not. It's not gravitational in nature. Yeah.
Okay. I see. I mean, but it has a lot of energy, and last time I checked, energy and mass are, have an equivalence relation, and that does dictate how gravity will behave. I mean, everything gets heavier that, I don't know if the properties of gravity will change, or, if things like that will happen.
Yeah, it's plausible that gravity might be involved at that energy. We don't know. I mean, once again, we don't know because experimentally we can't whack the Higgs field that hard. Then we would know, but I don't know if we want to try that. Obviously. So yeah, at the end we don't exactly know what happens, but it's just speculation.
Yeah. Is there any I guess speculation now how hard you'd have to whack the Higgs for it to go over this hill, or is that even debatable?
Yeah, I think you can roughly calculate where the turnaround happens, and I think I don't quote me on that. I think it's like 1 billion, 1 trillion times what we have right now. But it's very large. I'm sure. I can perhaps find it on Google. Let's see. Can find some papers real quick. Yeah, it doesn't say, but anyway, it's very, very large. Oh, it's 10 to the 12, 10 to 10. Yeah, about 10 billion. 10 billion. What the Higgs field is right now, just 10 billion folded, you know?
Yeah. Also, audience member corrected us about Shiva and says Brahma is the creator and Shiva is the destroyer. So just just want to issue that correction. Okay, and there's a few audience questions. One of them seems tangential, so I'll probably ask it towards the end. Um, but yeah, I think we're basically nearing the end of our discussion. Is there, I guess, anything you want to leave the audience with, like any words of wisdom that this death bubble has taught you in life?
Yeah, I mean, but let me reiterate that all this is speculative. You know, a lot of physicists probably don't believe this extrapolation because it's ridiculous. We can maybe look around the Higgs field by like, you know, 1 to 2 units, like a few units, and we're extrapolating what we see right now to 10 billion units out. I mean, that's ridiculous. It's almost like hiking. You take 2 steps and you're trying to predict whether there's a cliff, you know, in 3 miles and so forth. Like that's insane. We don't believe this level of extrapolation. But it is intriguing to learn that it's a plausibility. You know, our universe can be metastable and that our existence might not be guaranteed. We might, at the end, all be transient being. Well, of course, this is going to be way after the sun goes red giant and Earth will be destroyed anyway. But even just beyond that, right? Like even the universe, it's not guaranteed to be forever. Although we already know that there's a heat death and whatnot. But this just like solidified the fact even more. So I think it's another lesson, you know, that physics always humbles ourselves, right? Like we are nothing in this cosmos, and the best we can do is just, and there's nothing that's permanent. And the best we can do is just cherish the special, perhaps metastable state that we have.
Actually, this gives rise to another question I wanted to ask. Say you look far ahead in the universe, and the heat death has happened. The universe is nothing but a dilute gas of photons, and then this death bubble thing happens. Would that mean like particles would just come out of like existence, or like if you just had nothing but photons, like does that mean anything?
No,
Like,
no.
is the death bubble meaningful if there are no particles?
I think new particles will be created. This will be kind of the second layer of creation, right? It was quiet because all the energy is already stored in the Higgs field. But maybe the universe expanded and cooled down, and the Higgs field, you know, but never tap into the energy in the Higgs field. But when this cataclysm happened, you know, the Higgs field will unleash its energy once more. And maybe if the universe had a goal, maybe that is the end goal. Maybe we are just a means to an end. Who knows? If you like to believe that, maybe the universe, there will be even more beautiful structures when that happens. So we don't know. Yeah, but in some sense, there will be a second level of creation, almost kind of like our destruction will be maybe the creation of something else.
Yeah, I actually, another question I had is, you mentioned this analogy between like taking 2 steps and it's like you're looking out, miles and miles, like you're trying to extrapolate miles and miles ahead what, the landscape looks like. What, obviously extrapolation will be able to like, what am I trying to ask? I'm essentially asking like, what is the purpose of extrapolating that far? Like what does that help you do? Like there's some trade-off, like making this extrapolation allows you to maybe make some kind of prediction or something. Like what is the purpose and usefulness of saying like, oh, there's a cliff, even if we can't like see that far ahead and it's like a billion steps or a billion units or something like
I mean this is, I guess, just pure curiosity, right? Like physicists can do it, so why not? I mean, the prediction could be completely wrong, and many people think that it's totally bunkers. It's completely wrong. But if you just do this exercise, you know, you end up concluding that there might be a cliff, right? But of course, to really see it, you need to like build the next generation of colliders, which might be very, very expensive, and just whack the Higgs field hard enough to see exactly what that shape looks like. Then you can extrapolate a little bit further. But it's unlikely we'll ever get 10 billion times what we have right now. So in the end, this is always going to be a game of extrapolation, you know. But it's I don't know if this is sort of the boundary of science, right? Like if can we ever confirm such a thing? Like if decay were to happen, we're dead. Like so you can't really confirm it. And if you try to whack it hard enough, you probably can't whack it hard enough anyway. But if you do, I don't know if you want to whack it that hard, because there's always a danger too, right? But I don't want to discourage people to thinking that the Large Hadron Collider will destroy the world. It does not. Okay, like
yeah.
So, but anyway, this is just curiosity, I would say.
Yeah, I'll get to training. I'll start lifting heavier weights, and maybe one day I'll be able to do it. Okay, so one audience question I asked before we wrap up is do you endorse the archive in GRQC? I don't understand what that question means.
Oh, yeah. I think archive used to be that anyone can post, but now you have to have academic affiliation. Unfortunately, I do not have academic affiliation, so I cannot endorse any article on archive. I probably have to ask my colleague if I publish any paper to get an endorsement, but no, I don't. I cannot endorse.
Okay. That makes more sense. I thought it was like a concept or something or idea. But anyway, okay. Anyway, so that I think that's all the questions we have. So on that note, I want to thank you for joining us, and we'll see you all next week.
Yeah, thank you, and see you all.
Yep.
Bye-bye.